Hello, friends! I'm Clay, the adventurous Clay. Get ready! We're going to explore a world full of mysteries and surprises.
The Earth was formed through a series of complex astrophysical and geochemical processes that took place over billions of years. Current scientific understanding is based on the most widely accepted model, the solar nebula hypothesis, which explains that our solar system, including Earth, was born from a giant rotating cloud of gas and dust known as the solar nebula. This process involved crucial stages, beginning with the gravitational collapse of the nebula that formed a young sun at its center, followed by the development of a protoplanetary disk where planets were born. Within this disk, microscopic dust particles began clumping together into larger bodies through a process called accretion, which eventually formed planetesimals and planetary embryos. Countless massive collisions at this stage generated enough energy to melt planetary material, triggering differentiation processes in which heavier elements sank to the center to form the core, while lighter materials formed the mantle and crust. In addition, key events such as the giant impact hypothesis are believed to have led to the formation of the Moon, Earth's only natural satellite. Modern understanding continues to be refined by new discoveries, too. This report presents a comprehensive narrative of Earth's formation, integrating established models with contemporary insights that continually reshape our understanding of the origins of the planet we inhabit. From a giant nebula to the birth of the solar system, the formation of planet Earth was not an instantaneous event, but rather the culmination of cosmic evolution spanning about 4.6 billion years. This story begins with the initial conditions of the universe that laid the foundation for the formation of stars and planets. The matter and energy that shaped our solar system are thought to have existed since the early cosmic events, such as the Big Bang, which spread matter throughout space, and the supernova explosions of massive stars, which played a crucial role in creating the new elements needed for rocky planets like Earth. The most widely accepted scientific model for the origin of our solar system is the solar nebula hypothesis, also known as the nebula theory. This theory states that the solar system originally formed from a giant, slowly rotating cloud of gas and dust known as the solar nebula. This enormous cloud, primarily composed of hydrogen and other molecules, gradually cooled and contracted under the influence of its own gravity. As the nebula contracted, its rotation sped up, a process that can be physically compared to an ice skater pulling in their arms while spinning to increase speed. This rapid rotation caused the mass of gas and dust to flatten, forming a significant segment of energy. At the same time, most of the material was drawn into the core of the cloud, where it became giving rise to the sun. The remaining material surrounding most of the solar rotating disk, known as the protoplanets. In-depth analysis of early theories such as the nebula theory, the protoplanet theory, and the protoplanet theory shows that they are not mutually exclusive but rather complementary, merging into a single evolutionary narrative. The nebular theory provides the overarching framework for how the giant gas cloud collapsed and rotated. The protoplanet theory details how clumps of gas and dust within the disk became the seeds of planets. Finally, the planetesimal theory explains how solid grains formed within this disk eventually collided and merged into larger bodies. Thus, modern understanding integrates insights from each of these theories into a coherent model. The rotating nebula formed a disk nebular theory, from which planetary seeds emerged protoplanet theory, which then, through accretion, developed into solid grains and ultimately planetesimal theory.